All right, let's start with some review from last year. All right, the first thing we're going to talk about is inertia, because the first law is the law of inertia. Inertia is directly related to mass. So the more mass an object has, the more inertia it has, the harder it is to change its motion. So first law is a body at rest remains at rest with the same motion and in the same direction unless acted upon by an unbalanced force. So when acceleration is equal to 0, your net force has to be equal to 0. We also represent net force as the sum of the forces, so you might see it written that way sometimes as well. So when acceleration is equal to 0, the F net is equal to 0. It goes the other way as well. If your F net is 0, that means your acceleration must be 0. All right, the second law. The second law is the one that has to do with the acceleration. So the acceleration of an object is equal to its net force divided by its mass. You may remember it as the net force is equal to mass times acceleration. We will be talking about the second law in terms of acceleration equals the net force divided by the mass. Now, if you're talking about a system, it's the total mass. So let's go ahead and add total on there. Remember, these little arrows on the top just indicate that those are vector quantities. All right, third law. The third law was that action-reaction pairs. So the force on object 1 by object 2 must be equal to the force on object 2 by object 1. Remember when you're doing third law that there were 3 rules for that. The force pairs are from 2 different objects. So they come from 2 different force diagrams. They do not come from the same force diagram. Okay, so the force on you, the force of gravity on you by the earth is a third law pair with the force of gravity on the earth by you. All right. Secondly, they are equal in magnitude. And magnitude is just a fancy word for size. And they are opposite in direction. So the earth pulls down on you, you pull back up on the earth, but because the earth is so massive, it doesn't feel the same type of gravitational pull as we do because we have a much smaller mass than when compared to the earth. All right, so those are the 3 laws. So let's talk about some situations you are likely to encounter in AP Physics C this year. All right, so the first one, let's talk about the normal force. So the normal force is that force that you get from a surface. So it requires a solid surface. And remember that normal means perpendicular. So whenever we draw a normal force, it's perpendicular to the surface. If you don't have a surface, you do not have a normal force. Okay, so if we just have a block sitting on a flat surface, then the force diagram is just the gravitational force going straight down, your normal force going straight up. If the sum of the forces or the net force equals 0 for this, then your normal force must be equal to your gravitational force. And we calculate gravitational force by taking the mass times gravitational field strength. If you're on an incline, we have to do those components. So on an incline, my force diagram, the gravitational force is still going to go straight down. My normal force must be perpendicular to the surface, so it should look like that. If this has sum of the forces equal to 0, then it must also have a frictional force here, because otherwise it would be accelerating down the ramp. We're going to do components, and I'll do a separate video of components because I know some of you didn't do that last year in your physics class. If you draw your y component of your gravitational force down the normal, then your angle is right there between the gravitational force and that component. And then your horizontal component goes parallel to the frictional force. Okay, and I'll do a separate video on those to walk you through it. So right now we're going to move on to a different situation. So let's talk about another situation. Let's talk about pulleys. So let me draw a line here so you know this is a different one. So pulleys, we did a little bit of these last year. So you have an M1 there. We have an M2 hanging. We did a lab over this. We're going to say friction is equal to 0 here. We'll talk about friction later. I will briefly mention the how to calculate frictional forces, but we're not there yet. So friction is equal to 0. So you need to find acceleration for this. You need to take the net force and divide it by the total mass of your system. So what that comes out to be is the gravitational force from M2 is the one causing this to accelerate. And then you have to add the two masses together. I know that's what's causing the acceleration because I can draw force diagrams. If I draw a force diagram for M1, I have a tension, I have a normal, and a gravitational. These two are equal to each other. If I draw one for M2, I have the tension force going up. I have the gravitational force going down. Now, this is not a case where the gravitational force is equal to the tension. Oops, sorry. Got too close to my little arrow. Did it again. Okay, so your tension is not equal to your gravitational force here, okay? So these right here are third law pairs. These two forces right here are not causing any acceleration, so the only force you have left is this one that is on object 2, which is equal to mass 2 times the gravitational acceleration. I will do some more problems like this, not next time, because next time you're going to do a lab, but the time after that, because it's confusing with the gravitational force and the tension. Remember, sometimes they're equal to each other. That only happens if you have 0 acceleration. If you have acceleration, the tension and the gravitational force are not going to be equal to each other. All right, another situation we'll be looking at this year are elevator problems. Okay, so elevator problems. You have lots of things going on here. So an elevator hangs from a cable. So when acceleration is equal to 0, my gravitational force and my normal force are equal to each other, or tension, it depends. If you're doing the person, it's a normal force. If we do this for the elevator, which I'm doing on this one, then it's a tension, tension, not a normal, because the cable has tension in it. Okay, so when acceleration is equal to 0, that tension force is equal to the gravitational force. If I'm accelerating upwards, then the tension is equal to mass times your gravitational acceleration plus the acceleration you have in the elevator. If we are accelerating downward, then my tension force is equal to the mass times the gravitational field strength minus acceleration. That all comes from the force diagram. The force diagram looks the same for all three situations, but your sum of the force equations are going to look different. So let's revisit those. So remember last year, I required you to tell me whether the sum of the forces equals 0. That means it's a Newton's first law problem. Or do the sum of the forces equal mass times acceleration? That means it's a second law problem. Then you do the sum of the forces for what's actually on your force diagram. So in this case, tension and the gravitational force. So tension minus the gravitational force. So if it's a first law problem, we would have 0 equals Ft minus Fg. That's how we get the tension equal to the gravitational force. If we are looking at a second law problem, that's where we get these two expressions from, okay? Remember, there's no equation for tension. You have to create the equation yourself from the force diagram. All right. Oh, I needed another blank page. I'm going to skip ahead for a sec. Okay, so we need to talk about an Atwood machine, and we'll be talking about the Atwood machine some more when we do weightlessness and perceived gravity. But an Atwood machine is when you have two blocks over a pulley. The one we saw previously with the block on the table and the mast hanging over the pulley, that's called a modified Atwood machine. All right, so an Atwood machine, so again, you can look at two different situations here. You can do this as a system or as individual pieces. So if I'm looking at individual pieces, the gravitational force on mass 1 is m1 times acceleration due to gravity with your tension going up. Over here for F2, it's gravitational force, it's m2g with the tension going up. So these are my third law pairs. It's really important when doing pulleys to decide the direction of motion and call that positive. So if I decide to call clockwise positive here, that means that's a positive force, that gravitational force on mass 2. It's a negative force on the tension there, which makes this one a positive force on the tension because that tension's going up and in that direction, and then a negative gravitational force down here. So what we end up with is you can do these with individual sum of the force equations. If I just do one sum of the force equation, and I have m1 plus m2, that's my total mass times the acceleration. These two forces here are equal to each other because they're third law pairs, so I just end up with the gravitational force on 2 pulling on the gravitational force on 1. So we end up with an expression for our acceleration as the gravitational force on block 2 minus the gravitational force on block 1 over mass 1 plus mass 2, or the total mass of our system. And then sometimes they will simplify this to say m2 minus m1 times g. They'll factor out the g, and then the m1 plus the m2 in the bottom. Okay? So that's how you get acceleration in an Atwood lab or in an Atwood machine. And like I said, we'll be practicing some more of these when we do our weightlessness, perceived gravity, that assignment into not next class period, but the class period after. If we want to look at the Atwood machine and get an equation for the tension, let me first assume that m2 is greater than m1 for this equation. So I can get the tension equation by looking at either one of these. It doesn't matter. So the tension has to be equal to m1, the gravitational field strength, plus A, and you get that just from those equations. Ft is also equal to, if I look on the other side, m2 g minus A, because of the direction we picked for positive. So my tension can actually be found by taking 2 times mass 1 times mass 2 all over mass 1 plus mass 2, because that's our total mass, times g. So if you want to try and derive this equation from the free body diagrams and these equations, you could be my guest. On the free response questions, remember you have to show all your steps. So memorizing these equations or having them written down somewhere won't necessarily help you with points. It could help you on the multiple choice, but you need to know how to get these equations from the situation because you're scored on showing all of your steps. All right, last but not least is the train. And by train, we're talking about objects that are attached by ropes here and then being pulled by a force. So I have two tensions here. You could have a train with a whole lot of objects on it. It's the same way. So again, you can do individual free body diagrams. So that one just has FT1 going to the right. This assumes no friction. M2 would be M2 times the gravitational field strength. It's got a normal force. Of course, these two are equal to each other if it's on a level surface and it's not accelerating vertically. I have Ft2 here, but that's equal to the force that's given. I have Ft1 pulling back. So here are my third law pairs. So if I do this as a system, I have my system total mass times acceleration is equal to that overall force right here, which is my tension on string number 2. So I can get acceleration by taking this overall force that's pulling on them and dividing it by the system mass or the total mass. You could also look at individually then. So if you needed tension 1, all of these blocks are going to have the same acceleration. So this has the same acceleration as M1, and they have the same acceleration as the whole train. Okay, there are very few situations where you have a block accelerating faster than another block that are attached to string, and we'll look at one of those probably as we review for the test. Okay, so that's how I can get my acceleration. Well then, if I do the sum of the force equations here, I end up with T1 is equal to M1 times the acceleration. So once I have solved for the acceleration, I can plug it in here and get that tension. And then the second tension can be found by taking the sum of the force equations, which is what do I want to say? Oops, I erased a little bit. The acceleration of block 2 plus the tension 1, because this is the total tension for both blocks. Tension 1 was equal to M1A, so I can plug that in if you want to see it broken down into an equation that's usable. So that tension number 2 is equal to M1 plus M2 times 8, sorry. Yeah, no, I was okay there. I'm starting to confuse myself. And it's also equal to this one. So you can set those equal to each other and come up with a final equation. So, where did I get lost here? I see what I did. I put a minus, that should be a plus. These are the same thing, and it's the same thing I got for plugging this in for that tension over here. Okay, so some different ways to solve the train problems. Remember, if you add friction, let's talk really quickly about the equation for friction. There were two types. Static means not moving. Kinetic means you are moving or sliding. Remember that this is always parallel to the surface, and it opposes motion. Except for in the case of traction, but we don't talk about that a whole lot. We'll talk about it if it comes up, okay? So static, not moving, kinetic is moving. The frictional force equation on your equation chart says that it's less than or equal to mu times the normal force. The less than or equal to part is for static friction. If you are doing kinetic friction, you actually have the frictional force equal to the coefficient of friction for the kinetic times your normal force. Now remember, this little mu, or this little weird looking u, is your coefficient of friction. Doesn't have any units on it, and it's different depending on what type of surface you are that you have interacting with each other. So coefficient of friction changes because of the type of surface you have. All right, so that's it for this video. I'll do, actually no, I'm going to show you a couple of examples. Actually, I'll wait and do the examples in a separate video so that the videos are not too long. If you have questions, send me a message, let me know. I'd be glad to help you out.